Hello, good evening. Welcome back to our live tutorial section. In this tutorial session, I'm going to take you through second order linear differential equations. So second order linear differential equations. So you're welcome, viewers. Please follow as I take you through this subtopic in differential equations. So when you say second order differential equations, in fact, second order linear differential equations, from the beginning of differential equations, you were taught order, right? So you know that order is the highest derivative you can find in any differential equation. Now you were taught linearity, where you will show that any linear differential equation is represented as P of t multiplying y prime prime plus, so let's make it this way. So for the linearity, let's make it so simpler for you to understand. So if order is the highest derivative, let me write it here, then linearity, just saying that you are going to have your derivative plus p of t, which is a function multiplying y, then all this should be equal to another function g of t. So this makes it linear. Whenever you talk about linearity, just have in mind that you are dealing with the linear equation, which is equation of the straight line. So you are going to have your derivative as well as a function multiplying what this y. This can be 0, this can be a non-constant function. So now let's come to second order linear differential equation, meaning that the order is 2. Whenever you hear second order, this means that the order you are dealing is 2. So meaning that we are in order 2. So at this point, you should be expecting differential equations with y prime prime, or you can say d squared y over dx squared, right? Yeah. So this is the basic thing we are going to talk about from the topic second order linear differential equations. So let's quickly move straight to the representation of second order linear differential equations. But before we move, whenever you talk about second order, we have two main types. So let me write two main types. So we have homogeneous, then we have non-homogeneous. So under second order linear differential equation, we have homogeneous and we also have non-homogeneous. Now let me write the general equation for second order linear differential equation so that you understand what I'm saying. So generally, any second order linear differential equation is represented as P of t multiplying y prime prime plus Q of t multiplying y prime plus R of t multiplying y is equal to g of t. So you can observe that we have our y prime prime indicating that it's indeed a second order because it possesses the highest derivative, which is what, 2. So it is second order, and it is being multiplied by a function p of t plus g of t multiplying y prime then plus r of t multiplying y is equal to g of t. So this is a general representation of second order linear differential equations. Now back to the types as I was talking about. We have homogeneous, then we have non-homogeneous. In the case of homogeneous second order linear differential equations, you are going to have this term here, which is g of t, to be equal to 0. You are going to have g of t to be equal to 0. And in that sense, you are going to have your differential equation being in only y's. So let's say y prime prime plus 2y prime plus y is equal to 0. So realize that it's homogeneous. It's homogeneous. But before I come to this, we also have this p of t. Remember, this p of t is a function, g of t is a function, r of t is a function. So we have a constant and non-constant. So constant and also non-constant coefficients. So let me write it here. So since the coefficient of our parameters in the second order differential equation is a function, this function can either be a constant function, in the case where here it is 1, this one is 2, this one is also 1, or it can be non-constant function where I can have p of t to be something like 2t multiplying y prime prime plus 3t squared multiplying y prime plus y is equal to maybe 0. So this is a non-constant coefficient second order linear differential equation. I even omitted the homogeneous. So we are just using the parameters within it to qualify or give it a name. So here it is non-constant coefficient and it is homogeneous because here is 0. So non-constant coefficient, homogeneous second order linear differential equations. But in this case, you realize that the functions p of t, g of t, r of t are all constant. That is, it's integer. It's not any function. And you realize that one, we call it a constant coefficient homogeneous second order linear differential equations. So these are some of the basic terms I just showed you. So on that note, let's go to the first part of our section. So under this side, we are going to tackle the constant coefficient homogeneous linear second order linear differential equation. So let me make it second order linear differential equations. So it looks longer, but I hope by the explanation I gave you understand every term within this statement. So it's constant coefficient homogeneous second order linear differential equations. So meaning that we are going to have p of t multiplying y prime prime plus k of t multiplying y prime plus r of t multiplying what y is equal to 0. The 0 here stands for the homogeneity, right? Then the coefficients here are all going to be constant coefficients. So a typical example of what you are going to do is y prime prime plus y prime plus y is equal to 0. This is a case or a situation where all the functions are equal to 1. So in that case, we have y prime prime, we have y prime, then we have y. So this is a typical example of a constant coefficient homogeneous second order linear differential equations. So now let's quickly go through what we have here. So per this topic, let's start to talk about how to find solutions to such problem. So let me go straight to how to find solutions to these problems. So I'm going to give you the various formulas and the expressions to find without any proof, since you need to get what you want. So you realize that whenever you have a second order, now let's draw an analogy here. Whenever you have a second order, it looks like a quadratic equation where you have, let's say, ay squared plus by plus what c is equal to 0. And you know that whenever you have a quadratic equation, you should expect two solutions. That is y1, y2. The same thing happens when you come to differential equations. When you talk about second order differential equation, then it means you should expect two solutions. That is your y1 and your what? y2. And since you are dealing with functions when it comes to derivative, you can say y1 of t, y2 of what? T. That gives us the two solutions of our second order differential equation. Please, I come again. If a first order linear differential equation results in just a single solution, then a second order, you're going to have two separate solutions. That is y1 and what y2. But we have a principle called the principle of superposition. So principle of superposition. So this principle is saying that if you're having any second order linear differential equation, then the solution to the differential equation, which is y of t, is always equal to a constant c1 multiplying y1 on t plus a constant c2 multiplying y2 of t. All that this means is that you are going to have two solutions for your differential equation problem here. So we will have y1 then y2, then after they will be superimposed to form the single solution of our equation. So meaning that generally the solution for every second order linear differential equation should have two main solutions, right? And you should attach constants to it. Whenever you are dealing with derivatives, you have to attach constant to it. You get to understand this better as we move on with our tutorial. So generally, let me make a general statement here. So generally, to solve any constant coefficient homogeneous second order linear differential equation, the two solutions, as I said, y1 of t is always equal to e to the power r1 multiplying t, then y2 is of t is always equal to e to the power r2 multiplying t. So now I have given you the general form of the solutions we should expect. Always, your first solution should be e to the power r1 t, your second e to the power r2 t, right? So from this expression, by superposition, I'll have my y of t, which is the solution to the second order linear differential equation, to be equal to c1 multiplying er1t plus c2 multiplying er2t, and this gives us the general form for the solution to our constant coefficients second order linear differential equations. So just have this in mind. Now the next thing left is to define the parameters within this solution. So I have given you y1 of t is equal to e r1t, right? Then y2 of t to be equal to e r2t, right? Now where from the r, where from the t? The t just stands for any independent function which we are dealing with. It may be x, so you can say y1 of x is equal to e to the power r1x. This is just the independent variable which is associated with our differential equation. It can be any variable, but normally with the general representation we just assume it to be t. So let's move on. The r here is coming from what we call characteristic equation. So characteristic equation. So every second order linear differential equation should have what we call a characteristic equation. Now, what is this characteristic equation? So let's see. The characteristic equation is giving us ar squared plus br plus c is equal to 0. Please pay attention here. I am saying that every second order linear differential equation should have two solutions, which are in the form y1 of t is equal to e to the power r1 of t, and the second should be y2 of t should be equal to e to the power r2t, right? And by superposition, our solution, which is the general solution, happens to be c1 e to the power r1t plus c2 e to the power r2t, right? Now, from here, we need r and we need c1, c2 in order to get our solution done. And I'm here to explain the r, the origin of the r here. How are you going to get the r when any differential equation, which is a second order in nature, is given? So that is why we have this characteristic equation here. And this characteristic equation possesses the r we want. Now, we're from the ABC of the characteristic equation. So the ABC you see here is simply the coefficient of our differential equation. So given any differential equation which is second order in nature as ay prime prime plus by prime plus cy is equal to 0, then the coefficient of the y prime prime, which is a, is attached to r squared. Then b, which is attached to the y prime, is also attached to the what? R. Whilst the c, which is attached to the y, is c here, right? So just have it in mind that we are taking the coefficients of the respective parameters of our equation to form a characteristic equation. So let's see how this will be done. Let me give a problem. So let's take this as our first problem. So first example. So for the first example, let's see. I have find two solutions of or to find two solutions to our differential equation y prime prime minus 9y is equal to 0. So I have y prime prime minus 9y is equal to 0, right? So we have to find two solutions to this. Now this is a second order and it's constant coefficient because we don't have any function attached to our parameters. So let's see. At this point, the first thing to do is to find your characteristic equation, which is always given as ar squared plus br plus c is equal to 0. And I told you that the ABC represent the coefficients of the dependent variable, which is the y's in it. Now, a corresponds to y prime prime, right? Because you have squared here. For that reason, we are going to have here the coefficient of y is 1, meaning that a is equal to 1. The coefficient of r, which should have been y prime. So here we have y prime, but it is 0. So you just say b is equal to 0. Then what about c? C equals negative 9, right? C is equal to negative 9. So at this point, I'm going to have r squared, the b is 0, plus 0r, then plus c, which is negative 9 equals 0. Then my characteristic equation becomes r squared minus 9 is equal to 0. And this, by the difference of 2 squared, I'll have my r to be equal to positive 3, then negative 3. Once I have my r, what do? I simply come back to my equations here. This, then this. Is that not it? So at this point, I will simply write my y1 to be equal to e to the power r1. R1 can be any of these, please. Whenever you are doing it, choose r1 to be any of your roots. So r1 can be 3, r1 can be negative 3, depending on what you prefer. So I'm going to have 3t, right? Then I'll have my y2 to be equal to e to the power negative 3t. And this becomes the two separate solutions they are talking about. See, the question said find two solutions. They didn't just say find solution 2. If they ask you that find the solution to the general equation, then you should expect the superimposed form of the solution. But in this case, you have been asked to find the two separate solutions. For that reason, we are just taking the y1 separately, y2 separately. And this is what we are getting. So this is basically what you should expect in second order differential equations. Moving to the next, as I told you that we have characteristic equation ar squared plus br plus c is equal to 0. This represents a quadratic equation which you clearly know. So if you have this being a quadratic equation, then meaning that the nature of the roots, let me write it, nature of the roots nature of the roots will affect our solution. Is that not it? Every quadratic equation is expected to give three main possible solutions. Three main, where we have the first one being real roots and at the same time is distinct, right? So this is real distinct roots. This is where you have x1, x2 being different. They are not equal. So whenever they give you a quadratic equation and you have x1 and x2 not equal or different, we say it is real distinct roots. The second possibility is a complex root. A complex root. You know, from complex numbers, that is algebra, you're going to have a solution where you have, let's say, a plus or minus root of bi. A typical example is you have a root like 2 plus or minus root 5i. This is a typical complex root. And this has two components. It has 2 plus 5 root I. Sorry, it has 2 plus 5 root 5i, then 2 minus root 5i. Then the third possibility is what we call the repeated roots. Repeated roots. So for repeated roots, you realize that you get maybe your roots to be equal to 2 and it's repeating. So 2 comma 2. So this is repeated roots. So depending on the nature of the root of our characteristic equation, we can have different forms of the solutions to our second order problems. In view of that, let's go to the first one. So the first section, we have real distinct roots. So real distinct roots. Right. So considering real distinct roots, how do we go about that? Let's take our first example. And I hope by now you know what we call initial value problem, IVP, right? So solve the following IVP, initial value problem. When we say initial value problem, all that we mean is you'll be given initial conditions attached to your equation. And that will guide us to find the values of our constants. So let's move to the first page. So real distinct roots, right? So real distinct roots. So for real distinct roots, as I'm saying, solve the following IVP, right? So with that, I'll have y prime prime plus 11y prime plus 24y is equal to 0. The conditions are y of 0 is equal to 0 and y prime of 0 is equal to negative 7. So this is the first example we are going to see. So under real distinct root, what makes it real distinct root? It's just because of the nature of our characteristic equation. So I come again. Here, what is the characteristic equation? The coefficients. So I have a to be equal to 1 because a is a coefficient of what? Y. So let me change the color to make distinction here. So let's say a is equal to 1. Is that not it? Because the coefficient of this y is 1. Now my b, which is the coefficient of the y prime, is 11. Then my c is simply equal to 24 from this side. Is that not it? So at this point, I'll get my 1r squared plus 11r plus 24 is equal to 0 as my characteristic equation. Having this is equal to r squared plus 11r plus 24 is equal to 0. So what is r? R1 will simply be equal to my negative 8 and R2 to be negative 3. Just punch this into your calculator and you get a root, so we move away. So you have R1 negative 8, R2 negative 3. And at this point, the next thing to do is just write your respective equations. So your first root, which is y of t, is simply equal to e to the power r1t, right? Then your y2, which is equal to e to the power r2t, will then be given as my y1 of t will be equal to e to the power, my r1 is negative 8, so negative 8t then my y2 will be equal to e to the power negative 3t. And this gives me the two separate solutions. But we are not done. The problem said solve the following IVP. And as I told you, if you are being asked to solve, then it means you have to find a superimposed solution, right? So for the superimposed solution, you have to add these two equations respectively with the corresponding coefficients. So at this point, you have y of t to be equal to c1 multiplying e to the power negative 8t plus c2 multiplying e to the power negative 3t. And at this point, we need to find c1 and c2 before our equation will be complete. So how do I find this? I have two initial conditions, that is y of 0 equals 0 and y prime of 0 equals negative 7. What does that mean? Meaning that if I replace this t here with 0, everything here should turn what? 0, right? Then if I differentiate this y of t and I put 0 there, everything here should be equal to negative 7. So let me do that for the first one. So meaning y of 0, when I put 0 here, will be equal to c1 e to the power negative 8 multiplying 0 plus c2 e to the power negative 3 multiplying 0. What am I getting here? Y of 0 is giving me 0 is equal to e to the power, here will be 0, so it will be 1. So c1 plus, this will be 0, c2. So c1 plus c2 is giving me 0, right? That is my first equation. Then when I come, I have to differentiate this because y prime of 0 is rather negative 7. So meaning y prime of t will be equal to, how do we differentiate this? C1 is a constant, so it's not affected. So you just take negative 8 to multiply it by it. So you get negative 8c1, then you bring the whole thing again. Here will be negative 3c2 e to the power negative 3t. And at this point, I'll simply put 0 at where t is. So y prime of 0 is equal to negative 8 multiplying 0, multiplying c1. Negative 8 multiplying c1 to the power 0, everything here will be 1. Minus 3, here 2, we get c2. So you know that y prime of 0 is what? Negative 7. Is that not it? I'll simply put negative 7 is equal to negative 8c1 minus 3c2. And that gives me my second equation. Solving these two equations simultaneously should give me c1 to be equal to 7 out of 5, then c2 to be equal to negative 7 out of 5. Because from the first equation, the sum should be 0. And I will generally write my solution as y of t is simply equal to, this is what I'm writing, my c1, 7 out of 5, e to the power negative 8t, then plus c2, which is negative 7 out of 5, e to the power negative 3t. And this gives us the solution for our real distinct roots. Let's kindly take one more example on the real distinct roots, then we move on. So example 2, right? So for this example, it says find the general equation. So find the general solution to the following differential equation. And this is the differential equation. Y prime prime minus 6y prime minus 2y is equal to 0. So we have to find the solution, the general solution to this problem. What are we supposed to do? First thing, characteristic equation. What is my a? My a is simply equal to 1, b is equal to negative 6, my c is equal to negative 2. Therefore, my characteristic equation becomes 1r squared minus 6r minus 2 equals 0, giving me r squared minus 6r minus 2 is equal to 0. When you solve this simultaneously, you should get a root which is equal to 3 plus or minus the square root of what? 11. You ask yourself, is this a complex number? No. From the complex number definition, you should have a square root of negative number amounting to I. In this case, we don't have any square root of negative number. So this is a perfect distinct root problem. Take note of this. So my R1 is simply equal to 3 plus square root of 11. My R2 is simply equal to 3 minus square root of 11. Is that not it? At this point, I simply write my y1 of t to be equal to my e to the power 3 plus root 11t, then my y2 of t to be equal to e to the power 3 minus root of 11 multiplying t, and these are the two separate solutions. But the question asks for the general solution, so you have to superimpose these two solutions, and you get your y of t to be equal to c1 multiplying e to the power 3 plus root 11t plus c2 multiplying e to the power 3 minus root 11t. And this is not an IVP. For that reason, don't expect to take off the constant here. This is enough for your solution. Now let's move to the second part, which is complex roots. Complex roots. As I told you that the nature of the characteristic equation will give rise to different forms of solutions, right? For that reason, we are going to have complex roots provided our characteristic equation gave rise to complex roots. So let's take example here. So for the example here, complex roots, I'm going to show a simple, not a proof, but see something. You know that generally y1 of t, which is the first solution, is always equal to e to the power r1t. Is that not it? Your y2 of t is always equal to e to the power r2t, right? At this point, you ask yourself, if the root happens to be a complex root giving us r12, which is equal to mu plus, let me make it lambda and mu, lambda plus or minus mu I, where this is your real part, then this is your imaginary part. Then I'll have r to be equal to this. Is that not it? So I'll just put e to the power r1 lambda plus mu I t. Then I'll have e to the power lambda minus mu I, then t. So with this solution here, I can take just a single one. Now let's see, you know from complex numbers that whenever you have, okay, first of all, indices will say that you have e to the power lambda e to the power mu I for this section, because they have the same base, you add the powers. So now I'm decomposing it. Is that not it? And from complex numbers, you know that e to the power lambda is here, and it is going to multiply. This is the same as cosine of the expression mu of t. Cosine of the expression mu of t. Is that not it? Then, so the t was multiplying everything. So this will be t, this will be t, because the t was multiplying. Then, plus sine of the expression mu of t from complex numbers. Likewise, here will give us e lambda t cosine of mu of t minus sine of mu of t. At this point, you know from some of the standard equations in complex algebra that if we add these two equations, our imaginary part will go this minus and plus. To realize that if we add these two solutions, y1 of t plus y2 of t, then this side will cancel. So you get 2 e to the power lambda t, right? Then cosine of what? Mu of t. Likewise, if you subtract then so when you subtract, then our cosine part or real part will vanish. So I'll have negative 2. I'll have, sorry, I'll have 2i. Remember, I is here in complex number. I sine, yeah, so 2i, then you have sine mu of t, right? So at this point, this equation can further be simplified, and the resulting solution, which is of our interest, is y of t is equal to c1 e lambda t cosine mu of t. So cosine mu t plus c2 e lambda t sine mu t. So this is a general equation you need to have in mind. Please have this at the back of your head so that you can recall it when needed. So always your first equation will take the cosine part, the second will take the sine part, simply. Now let's take an example so you see how this works. So taking an example, I have solve the following IVP. This is an IVP. So I have y prime prime minus 8y prime plus 17y is equal to 0, where y of 0 is equal to negative 4, then y prime of 0 is equal to negative 1, right? So this is an initial value problem which we've been asked to solve. This is an initial value problem which we've been asked to solve. So at this point, how do I solve this? You should be reminded that you are dealing with constant coefficient. So you just bring your characteristic equation, right? So you have your a to be 1, b to be equal to negative 8, c to be equal to 17. I'll simply have ar squared plus br plus c equals 0, amounting to r squared minus 8r plus 17 equals 0. Now what is my r1, what is my r2? If you put this on the calculator, you should get your roots to be equal to 4 plus or minus I. Therefore, my one root, that is my first root, 4 plus I, then R2, which is 4 minus what? I. These are the two roots of our equations, meaning you have a complex root. For that reason, you are going to have two different equations, and this will be the equation. You have y1 of t, as you remember from the general equation, to be equal to e to the power, that is c1, e to the power, then the lambda, that is the raw part, 4, will come, t, multiplying cosine mu, which is what? 1. So cos t plus our c2, e to the power 4t, then sine of what? This one to likewise t. So this is what we have here. So this is generally our solution for the differential equation. Okay, so let's continue. So at this point, we need to find C1 and C2, then we are good to go. How do I do that? I have my two initial conditions where y of 0 is negative 4, and y prime of what? 0 to be negative 1. So what is y of 0? Y of 0 is simply equal to, wherever I see t here, I'll put 0. I'll get C1 e to the power 4 multiplying 0 cosine of 0, right? Plus C2 e to the power 4 multiplying 0 sine of 0. At this point, you realize that y of 0 was given as -4. I simply replace here with -4 is equal to, this is 1. Everything will be 1, so C1. Cos 0 is 1, so we simply get C. Plus, this is also 1. I'll get C2. But remember, sine 0 is 0, so everything here is 0. So my first equation is C1 is equal to -4, equation 1. And that even happens to be the solution for C1. The second part is you are to differentiate our y of t. So my y prime of t, what would that be? If you have this is a long differential. This because we have a cosine of t, then you have exponential function. At that point, there are two different functions multiplying each other. We are going to apply the multiplication, that's the product rule. So this will be my u. So let me write it here. So my u is equal to e to the power 4t. U prime will be equal to 4 e to the power 4t. My v is equal to cos t. I'll have v prime to be equal to negative sine of t. And at this point, that is what I'm going to do. You know that it's u prime v plus v prime u. So in differential equation, you are basically representing what you have. We are basically applying what you did in calculus. So here I'll have my u prime v. What's my u prime? I'll have 4 e to the power 4t multiplying the v, which is cos t, plus, but here my v prime is negative, so minus sine t, then multiplying my u, e to the power 4t. This is for the first part, that is this side. Then plus, when I come to the C2 side, here C1 is multiplying everything here. C1 is multiplying everything here. So my C2 also open the brackets. At this point, I have to interchange some things here. So my u is still u, e to the power 40, but my v is now sine, right? So that one, I'll change this place. So I'll have my sine t here. When I differentiate sine t, I'll simply get cos t. So my u prime v, u prime is 4 e to the power 40. The v is what? Sine t plus cos t, then e to the power 40. So at this point, you realize that we are done differentiating. The next thing to do is to do what? Put in 0 wherever we see t. So y prime of 0, which is -1, will be equal to, when I put 0 here, C1 out bracket, 0 here, I'll get everything here to be what? 1. Multiplying 4. Cos t, when I put 0 here, I'll get cos 0, which is 1. So here I'm getting 4 here, 4 for this side. So let me make it colored here. So I'm getting 4 for this side. Sine t, what is sine 0? Sine 0 is 0, everything here vanishes. So I'm getting 4 for this side. Then the next thing is what? This side, plus C2. Whenever you see sine t here, everything vanishes to 0. I just focus on the cosine part. Where I'll get cos 0 is what? 1, right? Here everything becomes 1. So I'll get plus. So C2, everything here is 1. So I simply, let me change the color to blue. So I'll have C1 4 plus C2 1. Already I have C1 to be -4. So I can simply get C2 to be equal to 15. Right? Because -4, -16, we send it there, giving me positive 15. Once I have C1, C2, our work is done. Right? So let me clean somewhere here and write my final answer. So at this point, I'll have my final y of t, which is a solution to be equal to C1, which is -4, multiplying e to the power 4t cosine of t, plus C2, which is 15, then e to the power 4t sine of what t as a solution to our differential equation. So this is how we go by complex roots. Complex roots. Let's quickly go to repeated roots. Repeated roots. So at this point, repeated roots, as I told you that when your R1 is equal to R2 is equal to a particular figure, let's say A, then it's repeated roots. So when we ask, how do I go by repeated roots? So generally, if you have a repeated roots, the general solution is given as you have your first equation y1 of t to be equal to c1 e to the power rt, then y2 of t to be equal to c2, then you multiply t e to the power rt. So y1 of t, which is c1 e to the power rt, y2 is c2 t e to the power rt. So basically it's equal, but there should be a what? A difference. That is why we apply just this t here to show the difference, just a multiple or a factor, right? So our general equation y of t will simply be equal to c1 e to the power rt plus c2 t e to the power rt, and you are good to go. So at this point, let's take an example so you see how we solve this. So solve the IVP, giving us y prime prime minus 4y prime plus 4y equals 0. I have my first condition, y of 0 equals 12 and y prime of 0 is equal to negative 3. So what do? I simply write my characteristic equation, which is r squared. I'm not going to go through the normal process. So r squared minus 4r plus 4 equals 0. You realize that when you have this, our r is simply going to be what? 2. So r1, r2 is still 2. R2 is 2. The next thing to do is come and refer to your equation here, that y of t is equal to c1 e to the power, what's my r? My r is 2t, plus c2 t e to the power 2t. At this point, I only need to find my c1, c2, then I'm good to go. How do I find my c1, c2? Y of 0 from the initial condition here is equal to 12. So c1 e to the power 2 multiplying 0 plus c2 t, which is 0, e to the power 2 multiplying 0. Here everything becomes 0. This place I get here to be 1. So I'm going to get c1 to be equal to y of 0 was 12. c1 is 12. I come to y prime of t. What is y prime of t? At this point, doing some simple differentiation here, I'll get what? 2c1 e to the power 2t. But at this point, I have t e to the power 2t. A linear function, exponential function, I have to apply the product rule. So I'll first maintain my t and I'll differentiate this. So I'll get t multiplying t multiplying 2e to the power 2t plus where t I differentiate, I'll get 1. So e to the power 2t. Now, all this is being multiplied by c2. Take note. At this point, I simply put my y prime of 0 is equal to 2. Here is 0, right? So I'll get 2c1, right? And when here is 0, everything here is 0. Here I'll get 1, so I'll get c2. And it should be equal to negative 3 from this side. I have c1 to be 12, 24. I bring it here. I'll simply get negative 27 for c2. So at this point, my general solution is simply equal to C1, which is what? 12 e to the power 2t minus 27 t e to the power 2t as the final solution for our repeated roots. So basically, this is how we solve our constant coefficient homogeneous second order linear differential equation. That should tell you that we still have non-homogeneous to solve, right? So now the next part of our tutorial is the non-homogeneous, which I doubt we finish. So non-homogeneous. Oops. Before I start with the non-homogeneous, let's talk about something we call Wronskian. So let's talk about something we call Wronskian. It's very, very necessary before we go to non-homogeneous. Wronskian. And I hope you really understood matrices in algebra. So when we apply some matrices here, you should understand. So Wronskian, as I'm coming to introduce you to, is just a nice concept. If you have two equations, or if you have any linear equations, which is simultaneous equations of two components. So let's say y. So we have y naught, which is, so let me do it this way. Whenever I give you a differential equation, I give you two initial conditions. Y of 0 is equal to y naught, then y prime of what? 0. But here, let me represent it by its own functions. So realize that I have y of t, which is equal to y naught, then y prime of t, which is equal to what? Y prime naught. Meaning that if I have these two equations, which is y naught is equal to c1 y1 of t naught plus c2 y2 of t naught as my equation 1, and I have y prime naught, which is equal to y prime of t naught, which is also equal to c1 y prime of t naught plus c2 y prime 2 of c naught t naught. Yes, my equation 2. We can apply matrices to solve for c1 and c2 without going through the simultaneous equations we're doing. We know that if you have 2x plus 3 equals 1, then 3x plus 4y equals 2. Bring y here. At this point, we can use matrix and you write 2, 3, 3, 4. Multiplying xy is equal to what? 1, 2. And we can apply what you call Cramer's rule. I don't know if you remember Cramer's rule. So when you say Cramer's rule, we used to solve system of linear equations. Once you represent your system of linear equations in a matrix form like this with the xy components, then the next thing to do is that you find the determinant of 2, 3, 3, 4. So at this point, you just find the determinant of this. Then the next thing to do is you find so this is the general determinant. Then you have the determinant x, which is equal to, you put the solutions you have 1, 2 here to the x component. So I have 1, 2, 3, 4 as my the x. Then the y, which is equal to, so the 2, 3 here, I'm going to have 2, 3 representing here, it will maintain. So I'll have 2, 3, but my y part, which is the y, I'll put 1, 2 there. So what Clemens rule is saying is that our x is simply equal to the x over d. Then our y is equal to the y on d. So just take the determinant of the dx and the y. This is the same scenario I'm going to apply in the Wronskian. So in the Wronskian, here we have two equations, right? So the first equation I'm going to show you is, let's say y naught is equal to c1 y1 of t naught plus c2 y2 of t naught. Then you have another y naught, which is y prime naught for the second equation. So first equation, second equation will be c1 y1 but is prime of t naught plus c2 y prime of t naught as my second equation. So at this point, using the Clemens rule, we realize that this appears to be the solution part. So I have to represent this in a matrix form, right? So representing this in a matrix form, remember these C1, C2 are just some constants we associated with, right? But you choose the main functions. That is the point of interest. So let's see. You have, and remember C1, C2, they are the unknowns you are finding, because whenever we want to find a general solution for our differential equation, the goal is to find C1, C2. So the C1, C2 here represents x and y in the scenario I showed you below here. So my x and y is the C1, C2, which I have here. So I'm going to have my C1 to be equal to my dx. The dx, so first let me write my d. My d, which is the determinant, I'll have y1. So my total d is y1 of t naught. Then I'll have this side to be what? y2 of t naught. Then when I come down, I'll have y prime of what? Y prime 1 of t naught. Then here is y2 prime of what? T naught. This is my d. Then the dx will be what? I'll replace this place with what? My solutions. Y naught, y prime of naught. So y prime naught. Then I'll have, that has replaced it. So I'll have y2 t naught, then y prime 2 t naught. Whilst my dy is also going to similarly be what? y1 t naught, maintaining this side, y prime 1 of t naught. Whilst this side, I'll replace it with my y naught and y prime naught. That gives me the corresponding d, dx, dy. So my c1 is simply equal to dx on d. My c2 is equal to dy on d, where dx now is equal to what? Y naught, y prime naught, y2 t naught, y prime 2 t naught over my total d, which is y prime t naught, y prime t naught, then y2 t naught, y prime 2 t naught. So this is the same for my dy. That is for c1. Now one may ask, why should we find c1 using a Clemens rule whilst we can simply use our normal simultaneous equation? So we are interested in this term here, which we call the Wronskian. So the denominator, or I will say that the d here is what we call the Wronskian. You realize that depending on the solution we get here, so if this expression turns 0, our c1 will not exist. It will cease to exist, because our dx on d and our d is 0, we are going to get undefined. So meaning that the solutions for any differential equation will hold provided the Wronskian is greater than 0. That should be the principle interested here. So our Wronskian should always be greater than 0 to have a valid and a defined solutions of any differential equation. From this point, let's move on and see how you find Wronskian. So let's see. At this point, let's solve some example of how to find Wronskian. Okay, so let's find some examples of Wronskian, right? Now, before we even find some of the Wronskian, let's talk about linear dependency. Linear dependency. So now, you can have a system of equations being linearly dependent, or you can be given two equations, and the two equations will be what? Linearly dependent or linearly independent, right? So at this point, when you say two equations are linearly dependent, what does that mean? And when you say they are linearly independent, so what does that mean? So if I have, let's say, an equation, let me give some functions like 2t, then let's say t squared. If I want to say that these two are linearly dependent or linearly independent, I'll have to multiply an unknown, let's say c1, multiplying 2t plus an unknown c2 multiplying t squared is equal to 0. And when you solve this equation and you get distinct values for c1 and c2, then we say that indeed this particular two separate equations are linearly dependent. If c1 and c2 is equal and is equal to 0, it means that it's linearly independent. That is, they don't have any relationship with each other. But so far as you get c1 and c2 to be a valid quantity, which is maybe 1, 2, or any other, then it means they have a relationship. That is linear dependency and linear independency. So let's see what we are going to do in this part of our tutorial. So in this part of the tutorial, I'm going to give you examples here. So in this example, first of all, let's find this. So compute the Wronskian of y1 of t, which is equal to t neg 1, then y2 of t, which is equal to t to the power 3 out of 2. So how do you compute the Wronskian of this? You just quote your formula. Wronskian is just equal to the determinant of what? You bring your y1 of t, then under it is its derivative. Then here will be y2 of t, then y prime 2 of t. That's all. And this should be equal to, you just bring your t inverse. What's the derivative? Negative t minus 2. This is t to the power 3 out of 2. What's the derivative? 3 out of 2t to the power what? When you subtract 1, you're going to get half. And just solving this using the matrix, applying determinants, you multiply this by this, minus this by this. So I'll simply have t to the power negative 1 multiplying 3 out of 2 t to the power half minus t to the power negative 2 multiplying t to the power 3 out of 2. So negative 1 plus half. So after computing this, you should get an expression which is equal to 5 over 2 root t. So this is simply how to find the Wronskian of any two functions given. Just take note. If we find a y1 of t, under it you take a derivative, or y2 of t under it you take a derivative, and you get your Wronskian. But what's the importance of this Wronskian? I told you that the linear dependency here, you should get a value for C1 and C2 greater than 0, meaning they are linearly dependent. Then if you get linearly independent, it means that C1 and C2 are all zeros, and the two functions do not have any relationship with each other. So now, how do we apply Wronskian in linear dependency? How do we apply Wronskian in linear dependency? So So at this point, let's quickly go forward. So with linear dependency, as I'm saying, Wronskian, Wronskian against dependency. Now, whenever you find a Wronskian of two functions, y1, y2, and you happen to get 0, meaning that the two functions are linearly dependent. Linearly dependent. And when you find a Wronskian of y1, y2, and it's equal to non-zero, then we say it is linearly independent. Right. So from linear dependency, we can simply talk about it here. So let me give you some questions here. Now, let's see. Determine if the following function, sorry with my handwriting, determine if the following functions are linearly dependent or independent. Right? So I'll have my first function f of t equals cos t. Then I'll have g of t sine t. So is these two functions linearly dependent or not? Right? How do you solve it? You only have to find a Wronskian. So let's find a Wronskian together. You just bring cos t here, you bring sine t here, right? You find the derivative. What's the derivative of cos t? Negative sine t, right? Then this becomes what? Cos t. So the Wronskian is going to give me this times this minus this times this. Is that not it? So I'll have cos t minus sine t, which is the same as cos t squared plus sine squared t. And this is giving me 1. And once we're getting 1, what does that imply? Meaning that they are linearly independent. Linearly independent. Right? So meaning that they are linearly independent. Now let's take another example here. So let's see this example. Okay, so now let's hold on with the Wronskian. Then let's continue with the Abel's theorem. That will be the last part of our tutorial, the Abel's theorem. So once you are done with Abel's theorem, you meet another time and you go through the undetermined coefficient and the variation of parameters to find non-homogeneous differential equations. So for the Abel's theorem, what this theorem is saying is that whenever you find a Wronskian of y1, y2 of any function, this is simply equal to c e to the power negative integral of p of t dt. So check it again. Whenever you want to find a Wronskian of what? Wronskian of two functions, right? Is simply equal to c e to the power negative integral p of t dt. This is in a situation where you've been given a second order differential equation and you want to find the Wronskian of the second order differential equation, right? So here you wouldn't get it y1 and a y2 straight away. So let's see what I'm saying. I have this particular problem. T to the power 4 y prime prime minus 2t cubed y prime minus t to the power 8y is equal to 0. The problem is, without solving this equation, find the Wronskian of the solution. So let me write the problem. Without solving this equation, find the Wronskian of these two solutions. So this is where Abel's theorem is very, very important. So you just go to Abel's theorem, like y1, y2 is simply equal to your c multiplying e to the power negative p of t dt. So now what's p of t? From linear equations, whenever you make, so remember linear equations are y prime plus p of t y equals what? G of t. So what that implies is whenever you want to find the linearity, make the coefficient of your highest derivative to be 1. So in our case, you are getting y prime prime. So I'll just take off y prime prime minus 2t cubed over t to the power 4, which happens to be the coefficient here. I'm dividing through y prime minus t to the power 8 over t to the power 4. Then this becomes y is equal to 0. So I'll have y prime prime. This becomes 2t to the power minus negative 1 y prime. This becomes minus t to the power 4y equals 0. Now, what is my p? Your p of t is always the coefficient of your y. Sorry, the coefficient of your y prime. In the case of your second order. For first order, it will be the coefficient of the y. So I'll simply have my Wronskian to be equal to c e to the power integral of negative. So I have negative 2 over t dt. This is c. This is the same as e negative 2 ln t. Just revise your integral. Then at this point, you know that you put your t here, right? So when I put my t here, but remember the Wronskian had a negative here, so negative will multiply and you get positive. So c e to the power 2 ln t. I'll simply put my t here, c e to the power ln t squared. E and ln will cancel to be 1, so I'll have c multiplying t squared as the Wronskian, just applying the Abel's theorem. So we have to end here so that we meet another time for non-homogeneous differential equations. That is, you treat the variation of parameters as well as the undetermined coefficients. Thank you for being with me in this tutorial. See you another time.